Hello everyone, in this video I'll be explaining how to carry out a numerical analysis of steady simulation of a diffuser in ANSYS. So for this we are given this problem where we have to simulate fluid flow through a diffuser, alright, and we are required to carry out the analysis for turbulent flow and laminar flow, and we have to plot graphs of Reynolds number against the mass flow rates to show the relationship. We also plot a graph of pressure drop or loss against the mass flow rates at the diffuser inlet. We're also going to capture different contours like velocity, pressure, and mass flow rates. We streamline as well in ANSYS Fluent. And with all of the data that we would have gathered at the end of this simulation, we'll be able to write a report in standard formats using Times New Roman, font 12, from introduction to conclusion. And the report should not be more than 6 pages. Okay, that's according to the instruction. All right, so how do we start with this? First of all, we need to understand how the simulation works. So in ANSYS, if you are to do a CFD simulation, first you need a geometry, which is the physical model of what you're trying to study. And then we'll look at how we can create a mesh. So we create differential volumes that ANSYS will solve for and integrate over in order to find flow parameters across the entire volume. And then the simulation is where all the calculations are done following the basic laws that govern fluid flow. So the laws of the Bernoulli's equation, the conservation of mass, continuity equations, Navier-Stokes equations, and all that. All of those things are put into consideration in the simulation aspect. So first thing we need to understand is that we are given the laminar flow conditions. So we are given Reynolds number for laminar flow conditions. We're also giving Reynolds number for turbulent flow conditions. But ANSYS does not allow us to put in this input. We can't just enter the Reynolds number and ask it to do a particular calculation and give us a result. It usually works with velocities or pressure. You have to define either velocity or pressure at the inlet or at the outlets, either one. So we always have to state the inlet parameter or outlet parameters, which can be velocity or pressure. All right. In order to do that, we can make use of this formula for Reynolds number to get our velocity values for each laminar flow condition and each turbulent flow condition. So if you make V the subject, you end up with V equals RE mu over rho D, where RE is Reynolds number, mu is dynamic viscosity of the fluid, rho is the density, and D is the diameter of the pipe or the characteristic length of the solid material, right? And for this experiment, this simulation, we'll be taking this assumption. We'll be taking the dynamic viscosity to be 0.891 times 10 to the third power kilograms second per meter, and our value of density will be 1000 kilograms per cubic meters. So these are assumptions, and this density value is taken at T equals 25 degrees Celsius. So this is the viscosity. Rather, viscosity is taken, not density. Viscosity is taken at 25 degrees Celsius. At 25 degrees Celsius. I'm looking for my degrees here. 25 degrees Celsius. All right, so we need to know that. And in Fluent software, we're also going to specify this as our fluid material in the database. All right, so first we need to solve for V for each condition. So we need to find V1, V2, V3, V4 for the 4 different Reynolds numbers in the laminar flow condition. We also find V1 to V4 for the other 4 different velocity for the 4 different Reynolds numbers that are given. All right, and we use our equation, just plug in your values. I think this should be -3. It's actually 10 to -3. That's a small error there. So it's 10 to -3. This is 10 to 10 to minus 3. Where's my operation symbol? Alright, I just take this as minus. Yeah, 10 to minus 3. Okay, 10 to minus 3. This 2 is 10 to minus 3. So sorry for that. Yeah, 10 to minus 3. The same thing for every single one of them. I think I can just copy. No. Okay, let me do it after the other. Minus 3. So we're going to solve for this. I'm getting my calculator. So for our first condition in the laminar flow, we have 100, Reynolds number of 100, the second Reynolds number of 500, Reynolds number 1000, and 1500. So we are going to solve this. Let me punch this in. 100 times 0.891 times 10 to minus 3 over 1000 times 0.04. That's 0.0002223. Let me just take 4 significant figures. 2228. So I have 4 significant figures here. Because it's very small. That's a very small value of velocity. The next one is 500. Okay, so I have 0.01114. I'm just taking to 4 significant figures so that I have something to plug in my calculation. The next is 1000. So this is 0.02228. And the next one is 1500. And 0.03341. 3341. Right? And then for the turbulent flow conditions, we need to use these values of our Reynolds number. One other thing I did not state was that I already have my values of L, L1, L2, D1, and D2 because we had to choose the diameters. We had to specify our own diameters of the inlet and outlet and the lengths of L1, L2, and L. Now the values for L1, L2, and L should come from this range. So L should be between 0.28 and 0.32. So I chose 0.03. L1 should be between 0.08 and 0.12. I chose 0.1. L2 should be between 0.08 and 0.12 as well. I chose 0.12. For D1, this should be between 0.04 and 0.05. So I'm just following the requirements to make sure that I'm following the question and I have something that is going to be within the range of values that is expected. Alright. So the D values are what I plugged in. I have 0.04 down here. So that's my D1, diameter of the inlet. So just have it in mind, that's where it's coming from. 0.04 is the diameter of the inlet. So we can continue solving for these. I have 5 times 10 raised to 3. So this is 0.1114. I'm taking 4 significant figures here. Then 10 raised to 4. Zero point 2228. Then 5 times 10 to the 4th power. That's 1.114. and then 10 to the fifth. 10 to the fifth. I have 2.228. So all of them are to 4 significant figures. And now I can pretty much start using these values to work now. So I have the velocities that I will put into ANSYS Fluent later on. But before I even get there, we have to start with our design. Alright, so now that we have these values, I think we are good to go. We can start designing. We have all the parameters we need. And then if you look closer at the material given, the outlet pressure is also stated. We'll get to this point where we'll need to consider this. And then we have used the Reynolds number, the equation for Reynolds number, to calculate the velocity at the inlet. That was what we just finished now. So I think we have all the input values that we need to start working. So the next step is to open our workbench, ANSYS Workbench, and then we design our model as the geometry of our problem. So let's get to that. So to find ANSYS Workbench, press the Start button or open the Start menu, however you wish to. And then in the ANSYS folder, there's a folder for ANSYS on your PC. If you have installed ANSYS, you will find many different applications. We are looking for Workbench. It's at the bottom here. It says Workbench 2025. So just a single click and you wait for it to load. Depending on how fast your PC is, it might take a few seconds. Okay, so it's starting up now. Yeah, so this is ANSYS Workbench. And to start with, we need to create our geometry. Like I said earlier, we start with a geometry, then the mesh and simulation. So we open Workbench, and then in the component section, because our system is broken down into this component, start with geometry. So I can find geometry here. You click and drag onto the workspace to create a standalone system. Now we have our geometry here. Very importantly, before we start, let's save this project. So I would like to save this project. Do I save it? I'll save it on my desktop just for simplicity, and I'll call it Diffuser analysis tutorial. Right. Okay, so it's saving that. You can always see what's happening in ANSYS Workbench down below at the top, at the lower left corner. So it says ready. It was previously showing saving project. So if you want to know if the software is currently doing any calculation or working on any process, you can see it down so that you don't get worried that it's freezing. So we have our geometry here, but we've not created any actual geometry. That's why there's a question mark there, because nothing has been created. So if you right click on this, you can either right click or double click. If you double click, it will take you to ANSYS Discovery, which is a new software for making geometries. But I like to use this legacy model. It's Design Modeler, which is part of ANSYS Mechanical. So let's use Design Modeler, because if you're using an older version of ANSYS, you most likely have Design Modeler. Even if you don't have Discovery, you should have Design Modeler. So now it says start seeing Design Modeler down here, so we know it's starting Design Modeler, and it will just take a minute or so, depending on your PC's performance. Okay, so this is Design Modeler, and yeah, it's fully loaded now. So for us to start our model, we need to determine the plane in which we want our design to be positioned. You can choose either ZX plane, ZY plane, or Y or XY plane. So if I want to model the length of this, okay, I can see the axis here. There's the green, red, and blue. If I want to follow this, the sketch I'm going to make, the profile that was revolved to make this sketch, is actually drawn in this green, red. Let's see, what plane is that? Yeah, it's in XY plane. So in our XY plane, click on that. I'll create a sketch. You can do that by clicking new sketch here, or you can also right click on this plane to look at the plane. Okay, let's just create a new sketch here first. Yeah, so I have a new sketch in that plane. All right, so I can rename the sketch. I can call it geometry profile or diffuser profile, since it's a diffuser, just for decency. Diffuser profile. So let's look at the sketch so that we can see directly in front of us. It's always important to check the units that we're working in. We're working in meters, so that's fine. Meters, angles in degrees, fine. Next thing is to start sketching. For you to start sketching, you come to the sketch tab, and then we have different sketch tools like lines, standard lines, polylines, and the rest. So I want to start with line tool. So click on line tool, and then we start with this. So our inlets, we start with the inlets. I know my inlets is something like this, is a vertical line here, and then I need another horizontal line for the first L1. L2 is not horizontal, it's slant, and then the last part goes like this, it's horizontal, and then finally comes down here, so vertical. All right, now there's another one I need to complete the sketch. Yeah, all right, now we need to dimension the sketch. You come to dimension, and if you are dimensioning horizontal lines, you click on horizontal dimension. If you are dimensioning vertical lines, if you are just dimensioning general lengths, so you can pick anyone. Right, so let's look at our dimensions. We know that this is a profile, it's half of the diameter, so considering that this distance should be half v1, we can edit v1 here. We chose our diameter 1 as 0.04, so we're going to enter half of that. That'll be 0.02. Sorry. Sorry, half of that will be 0.05, not 0.02, 0.05, 0.05. All right, so that's pretty, it's very small. It's very, very small. Okay, but we know that when we revolve it, the diameter will be 0.1 meters, so that's very small. And then the horizontal distance L1, it's calling it H2 here, but L1 is 0.1 meters. So I know that L1 is H2 here, 0.1. That's also very, very small. I think I need to zoom in. Yeah. Now L2 is actually giving us the horizontal distance of this slant line, not the true length of the line, but the horizontal distance. So I'm going to pick horizontal dimensions here, and I'll pick this point and this other point. Okay, H3, So that's L2. What did we choose? That's L2. 0.12. L2 is my H3, yeah. 0.12. Yeah, that's very small. Then the diameter of the outlets, we're going to enter half of that. And diameter of the outlet is 0.07. Did I make a mistake somewhere? My D1 was 0.04. So that should be 0.02. Did I enter 0.02? Vertical. Oh, this should be 0.02. Yeah. That should be 0.02. I think this is very small. Okay. Yeah, every other thing seems okay. Okay. So this diameter here, it's vertical distance, that's where I'll dimension it. It's called V4 and 0.07 divided by 2, that is 0.035. 0.035. Right, and that's not all. The horizontal distance of the line below, we also need to pick that. So it's this point and this point. Yeah. So this distance H5 is our L as the length of the entire 0.3. So 0.3. So everything should fit now. Let's see. Okay. So the scale, the problem here was with the scale. The scale was actually very large. Meanwhile, the object was very small, and it's ended up looking weird. Now I also want to bring this close to the origin. I don't want it to be too far. So the horizontal distance from this point to the origin, let me measure that again. Horizontal distance from, let me take this axis to that point. Okay, I want it to be very small. Right now it's 0.7. Let me make it 0.07 and see what it looks like. Okay, I can even make it smaller. Let me make it 0.05. Okay, so just have to bring it close to the origin because I don't want it to be too far. So I've completed the sketch. The next thing is to revolve. I think it's fully constrained now. Next thing is to revolve. So we go back to modeling and our sketch is highlighted yellow. Now we click revolve. The geometry has been highlighted, that's it. But the axis, what axis? We're revolving around our x-axis, so I'll select this x-axis here. Alright, and apply. So now it has been revolved, but I can't see the solid yet. I can only see some profile lines. In order to see the solid, I need to click generate. So I generate the new solid. Yeah, and now this is my diffuser here, looking pretty. Yeah. So I have successfully created the geometry. So next thing is to label the boundary layers. I want to label the faces so that ANSYS knows where the inlet is, where the outlet is, and which one is the wall. Now this is my inlet, this face. In order to select this face, I need to click select face. We have selection filter, so you can choose to select only points, or select edges, select faces, or select bodies. Now I want to select faces, so I click select faces, and then I can select this face. Now you right click on that face and come to name selection, and now to name that face as your inlet. So it's showing here as a name selection, but what's the name? I need to rename it. It should be the inlet, right? So I've named that as the inlet. Then I also want to name the outlets here. So this face, right click. Sorry, this face, right click. Am I on a different face? So I'm selecting faces. What is the name selection? Okay, I need to generate. All right. Yeah. Or geometry. Okay, something is wrong here, so let me delete that. So once again, let me try that again. Right click on that, name selection. Okay, the name selection should be inlets. Okay, so that's names, generates, done. Okay. So the problem was that I did not name it properly. I named it outside the window here, so I need to do that correctly next time. So we also have to name this face. Right click, name selection, and then you come here to change the name. This outlets. It's done. You can generate. So we have our inlets and outlets in our documentary. Then I also want to name this the wall, because the fluid is not going to come out of the wall. So you hold down Control and select other faces after selecting the first face. And the same thing, right click, name selection, then come here and type wall for the three faces and generate. Now I have my named faces. So if I come here and click inlets, the inlet is highlighted. If I click outlets, the outlet is highlighted. If I click wall, the wall is highlighted. So I have everything I need. I can check our workbench and you see that the geometry has been made. So now there's a check mark. So the workbench keeps track of how you are making progress in your simulation setup. So now I done the geometry. The next thing to do is to create a mesh. So we can close design modeler and then work on the mesh. So we have mesh here. Click and add the mesh, connect the mesh to geometry by just dropping it on the geometry. So if I release there, the geometry is connected to the mesh. Now I need to create the mesh. You double click on that to open mesh. Right, and once again, if you check down here, you can see what's happening, starting mesh. So just wait until it's done. Okay, so now the mesh module is up and it has to import our geometry. So just wait. I think the geometry should appear. I think it's still running. Okay, yeah, so now it's fully loaded and this is our geometry. Now we need to create a mesh for this. To do that, let's check again. We can see, is it still loading? Okay, still loading. All right, yeah, so you can see our different name selections, inlets, outlets, and wall. Now we need to create a mesh. So click on mesh and then the mesh details, we'll see display style. We're using our geometry settings, of course. For physics preference, we're not trying to study a mechanical system. Like we're not trying to study like motion and machines, whatever. This mechanical, it's not exactly what we're trying to study, and it's not electromagnetics. We're actually studying CFD, so computational fluid dynamics. So we click CFD as our physics preference. And what solver we are using? ANSYS Fluent. There are different ones, but ANSYS Fluent. our element size, I'll leave this as the default. It's just telling you the size of the mesh, that's the differential area that's, yeah, that's going to be used for the calculations. The smaller the mesh, the more accurate your result will be, but it will take more time to process and compute that simulation. Then the mesh sizing, let's see. I think we can just leave this as the default. Because the geometry is small, is a small size, I'll have to create the mesh to see how large the mesh is, and then I'll tell if I need to reduce the mesh size or not. All right, so let's just create that mesh, generate mesh. Let's see. Okay, yeah, so I can see the mesh we have here. There are different mesh methods. I didn't show that, but I think this is quite nice. The automatic setting already works well. The mesh sizes are not too big, and this is a multi-zone mesh, not a tetrahedral mesh. So I think in the settings we can choose the kind of mesh we want. So if you right click on mesh, we can see insert. We need to insert our inflation, because there has to be a boundary layer. When the fluid is flowing, the part of the fluid that's very close to the wall actually sticks to that wall. So we have to consider that property. All right, so geometry selection, we select this geometry. So press no, the boundary is to the wall. The boundary is around the wall. All right. Okay, so I selected the name face as my boundary. The inflation option, smooth transition, maximum layers. I think this is okay. Yeah. So I'll need to generate my mesh again with the boundary layers. Yeah, so now I have it has changed the mesh size. So this is a tetrahedral. Let's see. Okay, so what happened there is that I said fission. ANSYS, the software decided to automatically choose this mesh style. So I'm going to change the mesh style. This will actually work, but it's like too defined for the simple system. We are just doing a simple diffuser simulation. So a cubical or prism shaped mesh would work better than this one here. I mean, without using a lot of computational resources. So we come to mesh, insert, method. So the method of the mesh that we're using, we are applying the mesh to the entire geometry, and the method, it's saying automatic, so that's why it was choosing by itself. But we don't want to use automatic method. We want the multi-zone mesh. All right, can leave all this as default, and then we generate our mesh again. So let's see. It's going to take time to generate mesh and also generate the boundary layers that we've defined previously. Okay, yeah, so this is a multi-zone. This is a multi-zone mesh that we need. And I think the mesh size is fine. It's not so small or too big for the entire system. So this should work well. So we have defined the mesh, we have defined the boundary layers. What else do we need? Contact sizing, face mesh. Okay, I think we have almost everything now that we need for a system. I think we can move on to ANSYS Fluent now for our simulation. Yeah, and I'm not actually going through the details of setting all the parameters here because I just want a simple explanation on how to carry out this project. You can actually choose the growth rates of the mesh, the growth rates of the boundary layers that we've created, and so many other things that we can specify. But I'm going to work with this as this right now. So if you go back to Workbench, we can see that our geometry is basically done and our mesh is done as well. So we have everything we need to move on to Fluent. So we click and drag Fluent to connect it to the mesh that we just did. So Fluent will import the mesh. Now we have our setup. We can close mechanical. We can close that. Now we need to set up Fluent to tell it update the mesh. Okay, I need to update the mesh. So I'll right click on this and update. Okay, so now the mesh is updated. We can run the setup again. So now this is going to open Fluent and be able to set up our system for Fluent. All right. So how many server processes? This depends on your machine because Fluent runs locally, not online. You have to tell it how many processors that you want to use in your system to run the machine. So I have 4 processors on my system. So I think I'll just work with two out of the 4. I can use 3 if I want. So just make sure you don't exceed the number of processors you have on your system. So I'm using a pretty old system actually. It's a Core i5 with 2 cores and 4 processors, but I want to use 2. Let me make it 3 since I'll use 3 out of, yeah, just to make sure that it runs well. I'll use 3 processes out of the 4, so I can start. Alright, so Fusion is loading. Yeah, I mean Fluent is loading. I like to say Fusion all the time. Fluent. Right. Okay, so in Fluent here we have this toolbar up here with different tools, and these tools are divided into different sections. So there's a domain where you define the system that we're actually studying. That's our domain. We can check the mesh, check the quality of the mesh, do many different things. The physics is where we define the conditions that govern the system that we're studying. What is the viscosity of the fluid? At what speed is it flowing at the inlet, outlet? We define all those things. Then you can create some user-defined parameters. So let's say we want to study for a particular variable that is defined by an equation. You can write something for that, and then we can solve the simulation problem. We can get our results here with our results tab. We have the view tab for different viewing settings and others. So I'm not really going to be working with this because everything is actually listed here in the outline view. So the outline view is basically everything you have from domain to physics to the user defined to solution to results. Everything is here on the outline. So I'll be following this sequentially, starting from setup to solution and results. So we know we are setting up our system. Here we have our view of the diffuser. There's a console. Now this console is very important. It tells us what's going on, and we can see the calculations that are being done or the results. We can also get our results from our console. All right, so if you go back to the system, we are studying laminar and turbulent flow through this diffuser. Very important to keep that in mind. So we have our model. For the model that we are studying a viscous model here. So we click on viscous. Let's double click. And then for laminar flow, we select laminar. Okay. It's a laminar flow system, and that's the model system we're studying. All these we are not interested in. we are done with the model. The material, is it a fluid or a solid? We need to tell Fluent. Currently I have air, but I want to create a new material. I want to create liquid water. So the name is fluid one. I can call it water. What type of material? Of course, is a fluid. Chemical formula is H2O, but I don't need to enter that. I can just come into Fluent's database. Water is the most common fluid in the world. So you can just come to the Fluent's database and you select water. There's definitely water here. So we have different fluids. You can see different chemicals, atomic nitrogen, period solid. We just need to select water from our database since water is there and it's liquid water. So this is liquid water here. And we can see the properties of water, density of water. It's constant, right? We are studying an incompressible flow situation, so we're not going to choose compressible liquid. It's constant, and the density here, we're actually using a different density. We'll be able to edit that later, but we're going to change some of these values because I stated before that in my assumptions, I'm taking the density as 1000 kilograms per cubic meters, and the viscosity, I also have to change the value of viscosity too. So we can change those values later on. But first of all, I want to copy the general properties of water. Let's copy that. Okay, if it doesn't copy, then we close. So now I have water. If I come here, I can see my fluid materials. There's water liquid. I select water liquid. You can see the name has changed, water liquid. The chemical formula is there. Now the density is here, 998.2, but I'm studying density at 1000 kilograms per cubic meters. And then my viscosity, I'm using viscosity at 25 degrees Celsius. The viscosity of water at 25 degrees Celsius is 0.893 times 10 to minus 3. So I need to enter it here, 0.0000893. So this is the same thing as 0.893 times 10 to minus 3. Alright, so this is my viscosity. So it's very important that you state the material properties and you specify exactly what you want. So I'll click change/create so that it will update the setup, and now I can close this. So if I come here, I'll find water liquid. I can delete air. Okay, air is still there, but I'm working with water anyway. So just so you know, that's the fluid I'm working with. Then the cell zone. Okay, now this is where I tell Fluent what particular material is each zone in the mesh is going to be made of. So I can see solid here, but it's not solid. Let me edit that. Okay, so the material is water liquid. This is liquid water. The zone name is liquid instead of solid. Let me make it liquid. Is there any motion? No, the water is just flowing down. All right, and it's not rotating. There is no rotation along any axis, so let's just apply. So yeah, if you can see now, it has changed to liquid. Then we have fluid ID 2. Then boundary conditions. This is where we set the velocity at the inlets. So at the inlets, inlet velocity, we right click to edit that. I'll just double click. So we are going to enter the first velocity that we calculated for our inlets for laminar flow. Since we're in laminar flow now, the first velocity V1 is 0.002228. So we copy this value, copy Control C, we paste it here as our velocity magnitude. So that's our velocity. The inlet pressure is not specified. We're not to specify any pressure at the inlet. Alright, so Fluent to calculate the pressure at the inlet, but we just enter the velocity, apply. So I've applied that and we close. And how I know is because I can check the type of the inlets it's a velocity inlet, so I only specify velocity at the inlet, not pressure. If it's a pressure inlet, you have to specify the pressure, but it's just a velocity inlet, so that's for that. And then the outlets. For the outlet, what condition do we have? Double click on that. Let's define the outlet condition. Now, if you check the material properly, we were told that the pressure at the outlet should be the atmospheric pressure, that is gauge pressure. And gauge pressure is usually measured with reference to the atmospheric pressure. So if the pressure at the outlet is the same as the atmospheric pressure, that means there's no additional pressure on top. So the gauge pressure is 0. So that's what our gauge pressure will be. It will be 0, which means we are working. So I'm not going to change this value then. It's just going to be 0. And there are other things here. Backflow reference frame absolute. It just says that if the fluid, for any reason, tries to flow backwards, the parameters for measuring, let's say the pressure of the fluid should be measured in absolute value, not with respect to the environment. So if there's a backward velocity that tries to, if the fluid tries to flow backward, the velocity will be measured in absolute value, not with reference to the other fluids that are flowing forward. So I think that's okay. Absolute. We leave that as absolute, and then gauge pressure, apply our settings, and then we close. So we have set our boundary conditions for inlets and outlets. For the wall, let's see. Yeah, the wall. I think there's a no slip condition at the wall. We need to add that so that it follows Newtonian fluid mechanics. So it's a stationary wall and no slip. Alright, so that's it. Nothing to set here. Close. So we are done with inlets, outlets, and wall boundary conditions. Next, let's see our reference frame. We already know where our origin is behind when we're creating the geometry. We put it behind, so we don't need to set a new reference frame. Named expressions. So now, since we are trying to find the total loss in pressure, we write an equation that is actually an expression that helps to calculate the total loss of pressure, but we name that expression total loss of pressure, and then Fluent takes it as an equation. Let's create a new expression here. All right, the name of this expression is the loss in total pressure. So loss total pressure, and we are going to enter a function, an average function. Alright, so in reduction, we're going to measure the average of the, let's see, yeah. I'm considering the absolute mass flow rate. That's the weight. Change this weight to absolute mass flow rate. And we are measuring, what we're simply saying, the loss in pressure is the difference between the pressure at the inlets and pressure at the outlet. So I want to measure pressure at the inlet minus the average pressure at the outlet. So average pressure at the inlet minus average pressure at the outlet. But this pressure is going to also be a measure of the energy of the fluid. And for that to be a measure of the energy of the fluid, it has to be a mass-weighted average. So we are simply saying how much pressure is entering the fluid, is entering the diffuser based on the mass of the fluid that's flowing through. So it's a mass-weighted average, and if you think of it carefully, the mass distribution is going to affect the pressure distribution as well. So the center of pressure will be at the center of mass, or slightly below the center of mass. All right, so it's a mass-weighted function. It's not going to be equal all around unless we are considering the static pressure, which is like volume-based. It's going to be an area weighted average. All right, so since we're interested in loss of energy, since loss in pressure is a measure of the energy loss in Bernoulli's equation, we are going to work with mass weighted average. So we consider the absolute mass flow rate as one of the parameters in our calculation. So the location, the location here is our inlet. So I'm going to enter inlets. For location, I can just put boundary zones. I have inlets. I can enter inlets there. Right. So what's expression here? You can measure so our expression is pressure, yeah, average pressure. So let's say variables, yeah, pressure, total pressure. We're interested in the total pressure, not just static pressure alone or dynamic pressure alone, but total pressure at the inlets. So we're looking at the average of total pressure. Let me take that back. Average of total pressure at the inlet due to its weight from the absolute mass flow rate, calculated from the absolute mass flow rate, minus everything that we have here, but we change it, minus the same thing again, but this time around it will be for the outlet, right? Minus the average total pressure through the outlets, yeah, as a result of its weight measured as absolute mass flow rates. Okay, so for the description, I can describe what this equation or what the expression is. Yeah, this expression calculates the loss in pressure from the inlet to the outlet. Or I can just say loss in pressure through the diffuser. It's just important so that when someone else is looking at it, the person will understand what the expression is actually doing. So, okay, I have defined that expression, so I should be able to find it here. So, loss without pressure. It is not a curvilinear coordinate system, no, so it's just rectilinear. We have x, y, and z. Now let's go to solutions, the method, how you're actually solving this problem. The scheme, we're using the simple scheme. The simple, what does it mean again? It's an algorithm for solving the fluid flow. I can't really go into the details, but that's what we're using. We're using the simple scheme. And then for pressure, we're using second order upwind, momentum, second order upwind. It's just to improve accuracy. Like I said, there are many things about Fluent. Explaining all the details will take a longer time, but let's just go there. So yeah, I'm using simple scheme. Okay, least square cell base, actually. And then for controls, any special controls under relaxation factor, pressure, this, okay. Report definition. Yeah, you can use report definition to create reports that Fluent will generate while the simulation is running. So if I wanted to track pressure at the outlet, track pressure at the inlet, keep a track on mass flow rate at the inlet, mass flow rate, those things are actually needed. I can ask Fluent to create a report. So I wanted to create a mass weighted average. Let me just say flow rates. We have flow rates here. I want to track the mass flow rates. Yeah, this is volume flow. I want to track the mass flow rates at the inlets. All right, so the name of this report should be inlet mass flow rates. That is going to create a report file, report plot, and I want it to be printed to the console as well, so that when the simulation is running at the end, it will print out the mass flow rate at the inlet. Okay, so that's one. I also want it to give me the mass flow rate at the outlets. Outlets mass flow rate Also print to console. Alright, you can define many other things. Now there are different ways of doing it. If instead of creating reports, I can also come down to the report. There's a report section in results where I can just extract the reports that I want. But if you want it this way, you can do it this way. I'm just showing. You can also do the same for pressure. If you want to get the pressure at the inlet, you can get that as well. So I can get an area weighted pressure if I'm interested in static pressure at the inlet and outlet, or mass weighted. So which one should I go for? Let's go for area weighted here. Then I'll use mass weighted in the report section. So for area weighted average, I'm looking at either static or let's take total pressure. All right, total pressure at the inlet. So I'll just say inlet pressure. I want to create a report for pressure at the inlet. Inlet pressure at the inlets. I've selected that face. Okay, and I also want to create pressure at the outlets. So let's outlet pressure. It's area weighted average total pressure coming out. Okay, so I have all these reports that will be created when this initial is running. So I have them here: inlet mass flow rates, inlet pressure, outlet mass flow rates, outlet pressure. Now just keep in mind the pressures here are area weighted averages. The results will be different if you are measuring mass weighted average, because the mass weighted average will give you information about the energy going through the system, whether energy is lost or energy is added. Actually, energy is always going to be lost, while the area weighted average just tells you about the pressure acting against the surface area of the diffuser. So that's a different thing. All right, so we have defined almost everything now. We can now initialize and run our calculation. So to initialize is like setting our starting point, like setting t equals 0. So it will start calculating from this very point that is set up. So we double click on that. We have the initialize task page. Why is it taking so? It's actually another step. If this one is taking too long, you can just right click on run calculation and then select initialize and calculate. So it's initialize and calculate at the same time. But I just want to show how to initialize first before running calculation. So we are using hybrid initialization. Yeah, initialize, and then you can see it's setting our starting conditions. All right, I don't think it's done yet. So it seems to have a pretty slow PC. I've not even started a simulation. My system is blowing hot. Alright, let's see. Should probably close this. Let's close some windows. Okay, it's done already. Then I also want to minimize. Let me reduce this to panel so that I have more space. I need to, yeah. I want to collapse that so that I can have more space. Okay, yeah, so now I have more space here. Then I need more space on my console. Let me have more space up there. Good. Okay, so it has been initialized. Now we can run our calculation. Double click on that and then you click calculate. Another option, like I said, you just right click on run calculation and then you see initialize and calculate. I need to do both of them at once without you clicking initialize and clicking run calculation. So now it's starting to run the calculation, and you begin to see values for each mesh being solved in the console, and then to also show residual plots and any other plots that we have defined in our definition. I didn't specify a number of iterations to solve. So it didn't actually solve anything. It just ran and didn't solve anything at all. So I should enter the number of iterations. We can set it to 1000. I'm thinking 1000 is actually too much for this simple problem, but I'll set number of iterations. Let me just put it as 1000. So we just see, okay. So it's going to solve the problem like 1000 times, and it will check for variation within the results for each step. The goal is to have very little change in results as possible. So we can stop the simulation once we notice that there's no change between one step and the next. All right, you can just cancel it because it has solved the problem. All right, so we run our calculation now with 1000 iterations. Okay, so now it's running, and you can see it's solving pretty quickly. We are looking at, okay, I can currently see, I'm looking at the graph for area weighted average pressure at the outlet. And if you see, it starts with a high value here, and then the slope is very steep. It comes down very quickly to a horizontal line. So once I see this horizontal line, I can see that Fluent has already calculated a steady final results here. And that was pretty fast. Yeah, it's done with all that. I think it's a very simple problem. Okay, the calculation is complete now. So we can see our residuals. It solved the problem to very low levels of inaccuracy. Residual is just the difference between what it was able to solve and what it should be if all the physical conditions were followed. All right, so it's like checking itself against the mathematics or checking itself against the physics. So this is like a measure of error, and we can see it's going down and going down. So we have very small level of error here. It's a very small value. Let me see if I can read one of these. It's almost 0.00001. That's very tiny. So our residuals are small. I can see 3 times 10 to minus 4. These are small error margins that are left behind. So we have very accurate calculations. And it has calculated our mass flow rate to be a constant value of 0.0028 kilograms per second at the inlet. Our mass flow rate at the outlet is also a steady value of 0.0028. It has to be the same, all right? So this checks out. The mass of fluid entering is equal to the mass of fluid leaving. Then the inlet pressure has been solved. Then we have outlet pressure solved as well. All right, now to get the values, instead of just coming to the graph and trying to figure out a value at any point, you can come to the report section. Report section, where is it? Yeah. In the report, under results, you have reports. And if you open the reports, you'll find different reports. We are trying to get let's start with the inlet and outlet pressure. And this is how you do the experiment. You run everything we just did every single time for every velocity value. All right, so I'm going to get my pressure. It is surface integral, right? I'm looking at area weighted or mass weighted average here, because I want to measure the energy flow through the system. Mass weighted average for total pressure at the inlet, and I also want to measure the outlet. I can select more than one. So at inlet and outlet, Then I press compute. So in the console panel, you can see down here, it has calculated the total pressure at the inlet, pressure at the outlet for our very first simulation. So if you think about it, we're going to have many different values. It's best to put them on a table. So I'll create a table in Excel where I'll populate the cells in that table with values of pressures, mass flow rate, and velocities. So I'm opening Microsoft Excel. Okay, so I'll create a new worksheet, and on this worksheet, on this spreadsheet here, I'm going to have my Reynolds number, my velocity, the inlets. I'm interested in the mass flow rates. Let me say QM at the inlets. I also want to see the mass flow rates. I want to record mass flow rates at the outlets. I'm recording the pressure at the inlets. I'm also recording the pressure at the outlets. And I'm recording the pressure loss, that is delta P, the difference between pressure at the inlets and outlets. Yeah, delta P. My pressure is in pascals, mind you. Right. Yeah, the pressures are in pascals. It's good to keep that here. I need to expand this. Pressure at the outlets. Then my mass flow rate is in kilograms per second. Mass flow rate at the inlets is in kilograms per second. So velocity at the inlet is in meters per second. Reynolds number does not have any units, so it's unitless. Let's leave that. Need to expand. Okay. All right, so our different Reynolds numbers, we need to enter them. I think we have we're starting with 100, 500, 1000, 100, 500, 1000, 1500. And then for the turbulent flows simulation, we have 5,000, 10,000, 50,000, and 100,000. 5,000, 10,000, 50,000, and 100,000. All right. So these are for the first four are for laminar flow. The next four are for turbulent flow. Okay. Laminar flow. And I can make this, let's say, up. Let's say up. Okay, so my first velocity at the first Reynolds number value was this. So I'll copy that. That's my first velocity. Let me just paste it as a text. Alright, that's my first velocity. And from what I got in Fluent, my pressure at the inlet, this is my pressure at the inlet. Inlet pressure and my pressure at the outlet is here. I need to copy that, put it on the spreadsheet. Now the pressure loss should be inlet pressure minus outlet pressure, but I already wrote an expression for that. So let me see what ANSYS did based on that expression. And it should be equal to the mass weighted, because these are mass weighted values. The calculation I did was also mass weighted, and they should balance out. That's how I know that I'm correct. So I come to loss total pressure here under named expressions, right click and compute. Okay, I can see down here it has computed loss total pressure. Let me copy and paste it here. Alright, now you can see if you subtract this from that, let me just pull up my calculator here. Let me take a simple calculator here. So if I say this minus this is equal to 0.0073, which is exactly what I have here, exactly the same thing. Alright, so I know that my simulation is correct and everything is the way it should be. Then I also need to get the mass flow rates at the inlet and outlet. I can get that as well. From the results we have fluxes. So in fluxes, let me double click on fluxes. I can get the mass flow rates at the inlet and at the outlet. Click on those two and click compute, and I have my mass flow rate at the inlet and outlet. Now the mass flow rate at the inlet should be the same thing as the outlet, because what goes in is what comes out, just that the outlet be negative, so that's the direction. So I'll just put them on the table as well. Paste that, paste that. Okay, so I have all my values here, and if they are looking like so many decimals, you can okay, let me just leave them this way anyway, they're not bad. I wanted to kind of reduce them to like 4 significant figures, but we can do that in Excel actually. You can just say Ctrl+1 and then numbers. You can select, okay, I can select decimal places, so let me just say 6 decimal places, and every value here will be rounded to 6 decimals, so I have 6 decimals, so that's okay. That's okay. I can use this to plot my graph easily. So, or if you want the original values, you can still go for the original values, which is not bad. So after that, we will need to solve again. We have gotten all that we needed. We need to solve again. But before we solve again, let's get our contour plots, our contour diagrams for the pressure and velocity and the path lines flowing through the diffuser. Okay, so to do that, we will generate graphics. Under results, we have graphics, then contours, right? And even before that, we need to create some planes, because we are going to draw the contour along the plane, horizontal and vertical planes. So where is the plane? Let's say monitor surfaces. I think I can create surfaces. Yeah, surfaces, then plane. So I'll create a plane on what axis? I want a plane on my XY axis, something that cuts through like this. So on the XY, on an XY plane. Yeah, and let me even call this, okay, I've created it, right? Yeah, I just want to, let me call it my horizontal plane. I think it's going to be vertical instead. Let me just call it vertical V plane. The XY is vertical. If you look at the axis illustration here, so that's my V plane. right? And then I'll create a new plane. Let me close this. Create a new plane. That's my horizontal plane. I'll call it H plane. This horizontal plane will be along the ZX axis. I can tell from these orbits, but this coordinate system that's showing here. So as my H plane is going to be my ZX plane. Alright, so you can see this. ZX plane, create, close. Let me be sure that's my vertical plane actually. Let me display. Alright, so that's my vertical plane. And that's my horizontal plane. Good. Okay. Why do I have that? Okay. Alright, so now I'll create contours. I want to create a velocity contour diagram. I'll call it velocity contour. And I'm going to measure velocity, the magnitude of the velocity on the horizontal plane and vertical plane. And let me add some contour lines to make it more visual. Alright, then that's all display. Yeah, so I can see, this is beautiful. I can see the velocity of the fluid flowing through from the inlet to the outlet. And this is one contour diagram. So this is it. This is how you create a contour diagram. Alright. Then I will need to save this contour diagram because I will need to create references later on. When we're writing a report, we need to add this contour diagram. So I will capture. If you come down here, you can click capture. I want to capture a JPEG, and it's going to be a colored image, a raster graphics. Let me increase the resolution. So I want high resolution. I'll make it 1920 by 1080, like 1080p. 1080. It's going to be in the landscape orientation, white background. Fine. So I would like to use this setting every single time. So I'll click apply and save. It will be saved in my desktop. Since my project is in the desktop, let me just save everything in the desktop. Why can't I see desktop here? So computer, let me find my desktop. Users, me. Documents. Maybe I'll just save it. Let me save it here then. So 5. Let me create a new folder. So this one I want to save it, and I'll call it. The name of the file will be velocity 1 for laminar flow. So this is my V1 console for laminar. Alright, so I click OK to save, and it's saved. So I have to do this every time for every single plot that I make. And then I'll create another contour for pressure. I want to create a new one for pressure. I'll call it my pressure contour. Pressure contour. And I'm measuring total pressure on the horizontal and vertical plane as well. And I'll save. Let me display that here. So this is what the pressure looks like. So let me save this image. So the same setting has been applied. I'll just save. and this time I'll call it pressure 1 laminar. Pressure 1 laminar. That one is saved. Then we need to create path lines. The path line shows the trajectory of every fluid particle flowing through the diffuser. Okay, so for me to create path lines, I will come to, okay, this is it here, path line. Path line is your, we don't have streamlines here in Fluent, but we have path lines. So I will create a new path line. So this is my path line plots. Alright, let me just say path lines. I'll just call it path line plot. Alright, and I am going to color the particles. I'm going to color by velocity. I want to see how the particles are flowing, how fast they are moving through the fluid, velocity magnitude, and it's going to be from the inlets because they are all entering from the inlet. So the path lines will be generated from the inlet. So let me save and display that. Yeah, so these are, you can see the path that each particle takes as it flows from the inlet all the way to the outlet. Another thing you can do is to create an animation. So I can animate this process and I'll see the fluid moving. You can see this. So I can see how the fluid is moving through, which I think is very, very interesting. You can even save the animation as, okay, let me make it a continuous animation. Make it continuous. Yeah, so you can see the fluid flowing continuously. And if you want to save it, you just click, let me stop this first. You click Save Pulse Animation. Right, you can click Save Pulse Animation and you write it as a file. That would take some time though. But let me just save it. Pathlines plot. And I'll save it as pathlines 1. Is the animation, not the actual image, please. Pathlines 1. I'll call it laminar. Alright, so we'll just wait for that to be done, and then the most important thing is to actually save the image of the path lines. So that's what I'm going to focus on. So what it's doing is that it's taking snapshots of every point in space as the fluid is moving, and then to stitch all those snapshots together to create an animated short video, just an animation of the fluid flowing through. So that's what it's trying to do, taking shots of the fluid at different points along the diffuser. So you're done with this. Let me just no. Yeah, so what I actually want to save is this. This is the important thing to save here. So we save the image again, just like we've always done. I don't need to change settings. So I'll just save it. This time around, it's going to be pathlines 1 laminar. I need an image this time. Pathlines 1. Okay, so we've gotten all the contour diagrams and values for the first turbulent flow. You would have to do the same thing, exactly the same thing for every instance for the different flow regimes, for different values of Reynolds numbers. So you do the same thing for RE500. Just enter the velocity values that we've already calculated. Velocity values for the second one here are velocity is given. Yeah. All right. So for the next value of our velocity in laminar flow, to run the simulation again for that value, I'll just go straight to my inlet boundary conditions. We have boundary conditions, inlet. Double click on that, and then you change your velocity. Enter your new value of velocity. Click apply. And since we defined every other thing, we're still working in laminar flow condition. I'll just go to my solution, and then where we have run calculation, instead of running calculation directly, I will initialize and calculate. You have to initialize for every single simulation so that you start on a blank slate. You don't carry over values from the previous pressure calculations or previous velocity calculations. So initialize and calculate. It will clear the former data that you had, and then to start a new calculation with your new inlet velocity value. So once that is done, you compute your pressures at the inlets and outlets. Mass flow rates at inlets and outlets should be the same. Get your total loss pressure from the expression, named expression, and then get your pressure contour, velocity contour, and path lines. Just save the images, and you populate your table. So I won't be showing all those because of time. I'll be going to turbulent flow, how to set up system for turbulent flow. Okay, so after the calculation has been completed for the second time, I can already see the path lines diagram. So let me copy that here. If you can't see it, just come to your contours. Under contour, you have path lines here. So under path lines, you have path lines plot. You right click on it and click display, and it will display the path line here. So that's how you see your path line. And to save the path line image, click save picture using the same settings we've been using. This is path lines 2 because it's our second path line plot under laminar flow. Alright, so we save that. Close. We go to pressure control, the same as well. Let's see what's there. Okay. Then we save our pressure as well. We save it as pressure 2. Pressure 2 under laminar flow. And we do the same thing for velocity. Right click, select display, then here again capture our velocity 2 under laminar flow. And after all this, we have captured our pressure, velocity, and path lines. We now need to, let's go to turbulent flow situation. So in turbulent flow, what changes here is the model. It's the same viscous model, but you edit it and change it to turbulent flow. Now there's K epsilon for turbulent, there's K omega. You use K epsilon. It measures the energy of the eddy currents and the dissipation rates of the eddy flow. Alright, so we're using K epsilon, realizable K epsilon, and standard wall functions. I'm not going to change the model constants here. All these are physics and maths combined. Okay, so that's what we are using. And then we also have to change the solution method. So the way Fluent will solve this problem will be different. Remember, it's the same material as it did with water, as our fluid. Yeah, that should be gone. Should have air there. Should only have water. Anyway, I've defined it in the cell zone that I'm working on liquid, so there's no problem. So our boundary condition, the velocity is going to be different because we are entering the velocity at high Reynolds number. So for turbulent flow, the first velocity, what did we get from our calculation? We had 0.1114. So I need to, let me add this to my table in Excel. 0.114. Now this is what I'm going to paste in Fluent here. 0.114.
I'm not specifying pressure. The turbulence intensity 5%, viscosity ratio 20. You can leave these as default values. Apply. Okay, close. Our outlet pressure is still the same. It's still the same. Zero pressure, zero gauge. Right. And then the method. We have to go to the method. We work on the boundary condition on the word system. The method of solving is going to be different. This is simple, but for the turbulent kinetic energy, we are going for second order upwind, and turbulent dissipation rates, which is our epsilon, we go for second order. The kinetic energy is the K, so this is the K epsilon. That's where the K epsilon comes from. So once we've changed that, I think we are good to go. We can now initialize and run. I'll do those two at the same time by right-clicking, run, and then initialize and run. So what it's saying is that the previous data will be cleared, fine. So it's to do the calculation. And please, just for the second one, I did not gather the values for mass flow rates and pressure with the total loss pressure. I've already shown how to do that. So you repeat the same process for every single experiment that you run, every single simulation that you run. You run for this velocity, run for the second, run for the third, and that's how you keep going. So you, from the calculated values, you need to enter all of them while the simulation is running. The simulation is running in the background. I think you should be able to see. Oh, that will take some time. So our simulation is running here in the background. Let me copy this. This is my V2 for turbulence flow. V2 for turbulence. V3 for turbulence flow. You enter these velocities. Now that we've changed the parameters to turbulence flow settings. And then V3 for turbulence, or V4 rather, for turbulence. So this is the last one. Alright, so that's it. Let's see what's happening in Fluent. I think it's still calculating. Alright, so after gathering all the values like I've done previously, you will also save your pressure contour, your velocity contour, and the path lines. And then you will use all the values that you've populated, that you've used to populate your table, use them to write a report. You're going to write a report, just a technical report with your introduction, governing equations, the Fluent setup, your assumptions for the system. For example, in this simulation, I assumed that the dynamic viscosity is this value at this temperature. So I assumed that the experiment was run at 25 degrees Celsius. Just like you're writing a laboratory report for an experiment, it's all the things. Instead of writing aim, apparatus, and your process or procedure, we're going to write your introduction. You talk about your Fluent setup because that's the apparatus. The equations that are governing the experiment, that's like the theory behind the experiment. And then your procedure, just explain your mesh, what dimensions did you use, because everybody is in a different dimension. So what dimension did you use for your model? You also explain your observations. What did you observe from the trend on the table? You notice some trends. Okay, and we need to also plot a graph. Alright, so let me just show that now, because we have to plot a graph. I remember that. To plot a graph, you can use Excel to create a graph. It's not hard at all. Let me open something I've done before in the past. because of time, I don't think I'll. Because of time, I want the video to be short. It's actually it has taken over an hour now to record this video. Let me just create some. So let's assume that this. I don't want to come up with anybody. I'll just get some additional values from Fluent. Let's see. Okay, so let's assume that we have done our simulation for the different number of times, and we have these values. I also let me just fill up all these spaces. These are not accurate values. I'm just populating it with any, don't copy these. I'm just trying to show how you can generate a graph in Excel. So you want to plot a graph of Reynolds number against mass flow rate. I think that was the very first one that we asked to do. So one of the graphs that I have to plot here, the graph of Reynolds number against mass flow rate at the diffuser inlet. So this is my diffuser inlet. Mass flow rate at the inlet. This is it here. This mass flow rate at the outlet. So graph of Reynolds number against mass flow rate at the inlet will be this with this. So I use Control to select those two, and then I will insert a chart. It's better to use a what do you call it, scatter plot. Yeah, a scatter chart will always work best. Alright. So I'll insert a scatter plot, and it will just give you a vibe. Actually, you should get a straight line. The relationship between Reynolds number and mass flow rate is a linear relationship. It is not this. Because I didn't finish all the experiment because of the time. I don't have all the time to do that. My plot is looking like a sign, a square sign, whatever. It's just looking like something that is wrong. You can tell it's wrong, right? So this is not what I'm supposed to get. I should have a straight line if I have the correct values here. So you get the values from computing in Fluent your pressure at the inlet and outlet and then mass flow rate. I've shown that before. Let me just show you one more time. So if you want to get your mass flow rate, you come to Fluxes, double click on that, you see mass flow rate, and then you click compute, and it will compute your mass flow rate at the inlet and at the outlet. You also find it in the console. You have mass flow rate at the inlet and outlet. So you run your simulation every single time for every single value of velocity to fill every single row, and then you generate your pressure. You can change, you can edit this title. You can see Reynolds number, and if you can see, my Reynolds number is on the horizontal. So if I need to change that position, what do I do? Okay, so we come to let's right click on this. We can format, no, we can change chart type. Okay, we've already selected that. Let's see what this filter is here. Okay, that's possible. Let me see. Format axis title. I know we can change the axis title. How did I do that? Save as picture for chat here. No chat, no. Select data. Okay, yeah. When in the select data, you can switch the row and column. So if you switch the row and column, my Reynolds number will be yes. My Reynolds number is my column, and I have my. Now this is not the kind of chart you get. Like I said, you get a straight line. I'll show you the chart that you're supposed to get. So you should have something like this. So for pressure against mass flow rate, this is what I had. For Reynolds number against mass flow rate, this is what I got when I did all the calculations. So you should have a straight line for Reynolds number versus mass flow rate. And then for pressure, you should have a parabolic curve. This is a parabolic curve actually. So that's how to do the assignments. And then the last thing you need to do is to write your reports. And I don't think it's going to take another hour to probably do that and create a video. So you should be able to do that. Just your introduction, governing equations, your setup, present your table of values, your observation on the pressure change, observation on mass flow rates, and then ensure to put your charts, the pressure charts and pressure versus mass flow rate, that graph, and your pressure, what is it called? Pressure Reynolds number versus mass flow rates and pressure with mass flow rates. Those two those two graphs should be there. And then you should also have your plots, so the contour diagrams that we just created for each, these contour diagrams, you add them to your reports as well. With the path lines, they're very, very important. Please add them to your reports. So that's how to do the project.